Hello, everyone. Welcome to MACSMIN 2025. It's a great pleasure to introduce Professor Peter Olver, who will talk about reconstruction and signatures of three-dimensional bodies. Over to you, Peter, please.
All right. Thank you much, Vitaly, for the invitation to speak here. A little bit surprising because I don't work at all in crystallography, and the talk will not have much to do with crystallography. But anyway, Vitaly assured me that this was worth giving at this meeting. However, I do have one thing about crystallography. Let's see. At the very beginning, uh, this is a couple of pictures from the Galerie de Géologie et de Mineralogie in Paris. Well worth visiting for crystallographers if you haven't been there. And as probably most of you know, the science of crystallography began with the use of a certain tool named as the goniometer. And there's a picture of a goniometer, and the goniometer is just a very primitive tool for measuring angles. So the initial investigations into crystals were obtained by measuring the angles between the faces. Um, and I have a collaboration going on with anthropologists at the moment. Uh, I'm not going to speak about that, but I ended up, that's how I learned what a goniometer was. I was unaware of the tool before that. And while crystallographers, I guess, never use goniometers these days, people in tools in fields like anthropology, archaeology, and so on do use goniometers for measuring angles, but they're very imprecise. Uh, and although they're used quite a bit for analyzing things like broken bones, we decided with this collaboration to make a virtual goniometer. And we even tested this on a few crystals to make sure we were getting the right answers. So that's my one connection with crystallography that I have. All right. So now let me get to the subject of the talk, which is reconstruction of bodies in 3 dimensions from their images. And if I have time, getting to the uh, signatures part. So let's start. A body is just a compact region in Rn, but we're going to do 3 dimensions in the whole talk. So n is always 3. And I want to assume a reasonably smooth boundary for it. I'll have something to say about angles and stuff like that as we go along. Now, for simplicity, I'm only going to treat convex bodies here, but particularly in 3D, the non-convex is in some ways much more interesting, and parts of the body get hidden when they're being projected. And there's a lot of literature on that. I'll mention some people as we go along. But for simplicity, I'm going to do just the convex part because that's already of some interest. Okay, so the first part of the talk is reconstruction of convex bodies from their projections. There's a convex body, an egg. And so I'm going to do orthogonal projection. So this corresponds to photographing the body by a camera with an infinite focal length, or equivalently the shadow produced by a faraway light source, for example, the sun. One could also do projections with cameras with finite focal lengths, and the same ideas will work, but the computations are much more difficult. So we're going to stick to this. And let me briefly do the 2-dimensional case first before getting to the fully 3-dimensional case. So let's take a convex 2-dimensional body. Let C be its boundary. And take a line in R2, and then I'm going to project the body onto the line. And if you think about it for a second, you realize that what you get from the projection is just a line segment. So A and B are the endpoints of the line segments. Little AL and little BL are the endpoints, and capital AL and capital BL, they're going to be the lines orthogonal to the line L passing through the endpoints. So if you look at it, here's the picture. The body is in blue, omega, C is the outline. There's a line L. We project it and we get a purple interval, and then we take the 2 orthogonal directions to that interval, to the endpoints of that interval, and we get lines that are tangent to the body. Remember, I'm assuming smoothness for this. Okay. So if you're given this situation, then the body, or rather the curve, can be realized as the envelope of the collection of lines. So you take all possible lines L and you start drawing the corresponding orthogonal lines AL and BL, take the envelope of that collection of lines and you reconstruct the outline of the body. So that's the basic idea for reconstruction, is to use envelopes. So there's an example. There's the body. So those are all the orthogonal lines corresponding to lines in different orientations, and you see the body being reconstructed as an envelope of it. So we'll use the mathematics of envelopes to do the reconstruction. Okay, for simplicity, I'm going to assume that the origin lies in the interior of the body. And since it's convex, the outline of the body, the boundary, can be parameterized by a single valued, r is a single value function of theta, the polar angle. And L sub theta is going to be an oriented line passing through the origin at angle theta. If lines are parallel, they're the same projection, basically. So we only have to look at lines going through the origin to do this construction. And notice that if we go around by 180 degrees by pi, then we end up with the same line, but it's oriented in the opposite direction. So we get minus L. Okay. And then I'm going to use rho of theta and sigma theta as the radial coordinates of the two endpoints of the projection. So those are what I called AL and BL, little AL and little BL in the previous figure. Okay. And notice that if we go by the same reasoning, if we go by 180 degrees, we end up with minus rho. The endpoint at 180 degrees is just, say, the right-hand endpoint at 180 degrees becomes the left-hand endpoint at the other one, and vice versa. And so we end up with this as the connection. So we only need to know what rho of theta is. Okay. So here's the basic theorem for how you reconstruct the envelope of a collection of curves. So if you have a parameterized family of curves, so theta is the parameter. Of course, for us, theta is just going to be the polar angle, but it doesn't have to be. You can do it. Then their envelope is the curve Q of theta parameterized by this, where T, so T is the parameter of the curve, of the individual curve. Theta is the parameter for the family. So T of theta is determined implicitly by the conditions that the vectors dp by dt and dp by d theta are parallel. It's basically a tangency condition. If you go back and look here, what you see is on the envelope, the lines are tangent to the envelope at each point. And so if you write that, that means that the two tangent directions to the curves have to be parallel, and that's this condition. And here wedge is just the two-dimensional cross product, standard cross product, but in 2D. Okay, so that's the condition for the envelope. So you solve this equation, this implicit equation for t as a function of theta, and then plug it back into your parameterized family, and that gives you the envelope. Okay, so let's just specialize to our case. In our case, the line b sub theta perpendicular to L theta passes through the endpoint. That's parameterized by this. So rho of theta, remember, is the endpoint. T is just the parameter of the line, and theta is at the angle. So you get this formula for x and y. That's just the line parallel to the endpoint of the projection. Compute the derivatives. Easy calculus thing. And after simplification, you plug into the envelope equation, in other words, the cross product being 0, and you get this very easy equation. Rho prime of theta plus t is 0. So t is just rho minus rho prime of theta. You plug that in to the theorem, and you get the following parameterization of the envelope curve. So this is the boundary of the object being reconstructed by its projections, namely those the endpoints of those intervals. Okay, and this is an equation. It's probably not original, but it can be found in paper and books of Peter Giblin and Isaac Weiss. Peter Giblin is a professor at Liverpool, so there's a Liverpool connection to this talk. I think he's retired now, but I believe he's still in the area. Okay, so this is a local result, of course. You could reconstruct those parts of the body of a non-convex 2D body having the property that the tangent line does not intersect the body at any other point. That's the condition that the part of the body is not being occluded by another part. So it does extend to certain parts of non-convex bodies. You can't reconstruct perhaps the whole thing. Say if you had a body with a deep cavity, you couldn't figure out what the cavity is just by looking at the outside. Okay. Also, if you want to drop the smoothness assumption and allow corners, the corners of rho of theta correspond to corners of the body. In other words, the points where the derivative is discontinuous. On the other hand, straight line segments on the body, so if it's not strictly convex, it has straight line segments, those correspond to discontinuities of rho of theta. So one can build that into the reconstruction formula. Okay, so I want to do the same thing for 3 dimensions. So let me introduce a bunch of terminology, but it's much easier instead of reading the slide to look at the picture. So the body is that sphere, that kind of yellowish sphere. I'm going to project onto a plane, so P is the greenish plane. So when you project down to it, you get a convex curve because the body itself is convex. So C sub P is the outline. So the outline is what you get on the plane when you project the body. Again, remember, we're doing orthogonal projection. We have a camera of infinite focal length. Okay, if you take the cylinder that's orthogonal to P with C sub P as the outline. So this is not a circular cylinder, or not necessarily a circular cylinder, but it's a cylinder based on a convex planar curve. You get K sub P, that's the cylinder. That will intersect the body on a certain curve, and this is what's often referred to as the rim of the body corresponding to that plane P. So we have the outline, which is back down on P. That's the thing we see if we take a picture of the body with that as our camera plane. And the rim is what is the points on the body that correspond to the outline curve, the C sub P. Okay, so that's what's all in here. Other names for the outline are apparent contour, profile, or silhouette. The rim is sometimes referred to as the outline curve. Okay, so all the terminology is contained in this picture. Okay, and as with the planar case, so you vary P over all possible planes, and again, we're going to restrict to planes that go through the origin and assume for simplicity the origin is contained in the body. So we're talking about a Grassmannian mathematically. Then we get a whole family of outlines, and the goal is to reconstruct the body from that family of outlines. And as in the planar case, it's going to be given as the envelope of these outline cylinders. So you think of the P varying, you get different cylinders, they're all tangent to the body at on various curves. And if you take the envelope of that, you get a 2D surface, which is the body itself, or is the boundary of the body itself. Okay, so now you look in, so this is a bit more complicated, a bit harder to track down than the literature, but Google searches are always good these days, so you can track this down. So now we're doing the actual 3D cross product. I still like wedges for cross products for various reasons. So we're going to assume that we have a 2-parameter family of surfaces. So if you think about it, the planes P you could identify by their normal direction. The normal direction, the unit normal, is on a sphere, so there is a 2-parameter family of planes, all possible planes going through the origin. So that's the theta and the phi. Those you can think of as spherical coordinates, which they will be in our case. And then S and T are what parameterize, given theta and phi, S and T parameterize the surface. In the theorem, the surface can be very general. In our case, it's going to be the cylinder parameterized by S and T. We're going to assume they're non-singular. In other words, we can do these are nice smooth surfaces by the implicit function theorem. So we assume that dP by ds and dP by dt are not parallel. And similarly for dP by d theta and dP by d phi. In other words, this is a non-singularity condition on the family itself. Then the envelope is the surface parameterized by Q, and S and T are determined implicitly by the condition that all 4 of these vectors are coplanar. Or if you want to write it out, you can write it out explicitly in terms of cross products. So this is the condition for the envelope. This is how you reconstruct the body through this envelope construction. Okay. So in our case, we're dealing with spherical coordinates. So X, Y, and Z are the usual spherical coordinates. This is the mathematical convention for spherical coordinates, as opposed to the physics convention where the phi and the theta are reversed. It's interesting to go back to the history of how this happened. The physics one is actually older. When Laplace first introduced spherical coordinates, he actually used all kinds of letters for them. And then it kind of settled down to the physics version. But then later the mathematicians realized it's much easier to use theta because if you specialize to the plane, to the XY plane, theta remains the polar coordinate rather than having to switch them. Anyway, so that's my convention for spherical coordinate. So P sub theta phi is the plane with this unit normal on the unit sphere. And we take the following orthonormal basis of this plane. So I'm going to use an orthonormal basis. Of course, you have a lot of choice in the choice of orthonormal bases, but this one is particularly convenient. So U and V are given by this formula. And the outline curve, so because the origin is inside the body, the outline curve is a single valued function of theta and phi and determined by psi. So given theta and phi, the outline curve is parameterized by psi. Okay, so this is parameterized. Given theta and phi, this is what the outline curve is. It's parameterized by psi, given by this. In other words, it's a linear combination of the two unit orthonormal basis vectors. The outline cylinder is just taken by taking the outline curve, so that's the second and third term, and then also introducing a second parameter t that goes in the normal direction. So that just goes in the direction of the unit normal vector. And then we write out the envelope conditions, and after some simplifications, we end up that there is some scalar valued function lambda such that these three equations have to be simultaneously satisfied. Okay, so it's pretty elementary calculation, trigonometry calculation. You can solve for lambda and t, and you get this formula, and then you plug the values of lambda and t into the last equation, and you end up with this as the formula. So this implicitly defines psi as a function of theta and phi, the angles determining the plane, and this serves to parameterize the boundary surface. So there's an explicit formula, well, an implicit formula for the boundary surface, in other words, the reconstruction of the body from its outlines. For the reconstruction formula, if we take a point on the outline curve at a given angle theta and phi, the corresponding point on the rim curve is just gotten by using the value of t. Remember, we solved for t in the formula for the rim curve, for the cylinder. Sorry. So you do the value of t, and that gives you, given the outline curve, this enables you to easily reconstruct what the rim curve is. Okay, so that's that formula. So if you think about it for a second, as theta and phi vary over the unit sphere, they're the spherical coordinates, you obtain a doubly redundant three-parameter representation of the body surface. In other words, it's not uniquely determined. You get it determined kind of twice because you have two different sets of parameters. Each point P on the surface, on the outline, on the boundary of the object belongs to a one-parameter family of rims obtained by rotating around the surface normal. If you think back to that picture, so if you think of it as the plane is evolving, some of those planes will give the same point on the rim, so you get a redundant set. It's a one-parameter family of planes. However, even though this is redundant, in data-driven applications, one could practically utilize this formula to numerically construct the surface as a collection of points, point cloud, or from that a triangulated mesh. So this is practical. In fact, you got a lot more data from this than you will get just from a single parameter formula. Okay, here's a drone. We hear a lot about drones nowadays. Suppose, to get rid of this ambiguity, suppose instead of taking all the possible outlines, we fly a drone around the body and just get a one-parameter family of outlines. So let's suppose that the drone follows a flight path. I'm going to assume it's outside the body so it hasn't crashed. Okay, so S is, say, the arc length parameter of the flight path of the drone. We'll assume the drone camera is always pointed towards the origin. If the drone camera is pointed in different directions, then you have to adjust for that accordingly. But just to keep the formulas under control, I'm going to do that. So you get a one parameter family of outline curves instead of the two parameter full family of outline curves. The outline cylinders are parameterized by this, and then you get the reconstruction formula. It's a little bit slightly more complicated than before, but still eminently computable. In particular, if the drone went around an equatorial great semicircle, so in other words, it was in the XY plane, then you get this nice formula, the first nice formula. And if it goes on a polar great semicircle, so it goes through the North and South Pole or above the North and South Pole of the body, then or the sphere given by the spherical coordinates, then you get this as a nice formula. Okay, so these formulas, some of them exist in the literature, in particular the works of Peter Giblin, and others are there. Before I go on to the next part of the talk, let's see, I'm still good. I have about maybe 20 minutes still. Are there any questions about this before I proceed further? Wait for a second.
Peter, yeah, thank you. Could I ask if the main theorems are proved under smooth conditions?
That's right. So the main theorems are proved. The body has to at very least be C1. I think it has to be continuously differentiable. I don't think you need C2 to prove these theorems.
Mm-hmm.
Yeah.
May I ask if you maybe later will discuss, say, a piecewise linear case, say, in the plane, a polygonal boundary?
Right. So then if you're a polygonal boundary, so this is kind of a different problem. This is the problem of so the projections in that case are going to be polygons. So the question is, how do you reconstruct a polytope from its projections of polygons? And I'm assuming that quite a lot is known about that, but I don't know that literature. I haven't looked into that literature.
Okay, so your case is smooth.
Yeah, so my case is smooth, exactly, yes.
Okay, thank you.
Okay. Anything else before we go on? Okay, so now, of course, there's a group acting on it, namely the group of rigid motions. So this means that we can change coordinates, or equivalently, we can rotate and translate the body, and that doesn't change it. So there's a very interesting action on the outlines and the projections. And one of the things I got interested in, based on earlier work in 2 dimensions, was how do you find the invariance of that action, and how would you go about an invariant means of investigating this? So we're going to deal with the 3-dimensional Euclidean group, rotations and translations of 3-dimensional space. It acts on a body in the obvious manner, and hence it acts on its projections. And so the goal of the next part is to understand the actions and determine invariance. And it's a very interesting action of the Euclidean group. And for this purpose, I'm going to use the theory of normal forms and equivariant moving frames. So I'm going to do a little brief introduction to that, because that's what we'll use to understand this action. Okay, so by a normal form, we mean, so you're given a group, in our case it's the Euclidean group, and you use the elements of the group to put the submanifold into a distinguished position. So you put it in, so the definition of a normal form of a submanifold is you place its Taylor expansion at a point that you're interested in as simple a form as possible. And of course, there's a matter of choice. What do you actually mean by simplicity? Usually that means that as many Taylor coefficients as possible are 0, or if they're not 0, maybe they're 1 or 1 over n factorial or something simple. Okay. In linear algebra, normal forms are often called canonical forms. So something like the Jordan canonical form is the normal form of a matrix. But we're going to do it. In the language of equivariant moving frames, which I'm going to briefly mention but not go into the full details, normal form is equivalent to the choice of a cross section to the group orbits, or the prolonged group orbits. Okay, and the key remark is once you put a submanifold in normal form, any non-constant Taylor coefficients as functions of the original submanifold form a complete system of functionally independent basic differential invariants. So differential invariants are things like curvature and torsion of curves, principal curvatures of surface, Gaussian mean curvature, and so on. So one ends up with, by applying this moving frame theory or some way of getting things into normal forms, you also end up with getting all the invariants. And so you can investigate the invariant properties of the object. Okay. And moreover, the method of moving frame provides something that I'm not going to go into called the recurrence formula, but they're eminently computable that connects the basic differential invariants and their derivatives. So we'll see examples as we go along. The general framework, we're just given an m-dimensional manifold. For example, M is Rm. We're going to have submanifolds of a fixed dimension. So in our case, those are two-dimensional because we're dealing with, well, two-dimensional for the original object. The dimension of the outline will come out in a little bit later. And because we're going to look at differential invariants, in fact, the group is transitive, acts transitively, so there are no ordinary invariants. One has to go to differential invariants or some other type of invariance to get it. So we'll deal with jet spaces. There's nothing very complicated about jet spaces. They're just a formal way of talking about derivatives or Taylor series. And then G is going to be a Lie group. For our case, it's going to be just SE3. One can also do infinite dimensional pseudogroups, but that's a more complicated theory. Okay. And because the group acts on submanifolds, it also acts on their derivatives. So there's what's called a prolonged action on jet space. This is obtained by implicit differentiation. So this is eminently computable. I don't have time to go through the details of how you do the computations. I'm going to just show you some of the results. Okay, so a differential invariant is just an invariant of that prolonged action. In other words, the action of the group on the derivatives, say the tangent vectors, the second derivatives, and so on of the submanifold. And as I mentioned before, things like curvature and torsion show up very naturally as the most basic ones of these. There's also a collection of invariant differential operators. So in the simplest case of a curve, this is the derivative with respect to arc length. And these have the property that if you take a differential invariant and differentiate it, you get another one of higher order. And then one can ask, what about the algebra of differential invariants? So quite a lot is known about this nowadays, thanks to the moving frame methods, but there's still a lot of unanswered questions. But the basic result, this is like a Hilbert theorem for differential invariance, a basis theorem. It says that in all cases, or all reasonable cases, the algebra of differential invariance is generated by a finite number of differential invariants and obtained by invariant differentiation. So a version of this actually for finite dimensional Lie groups goes back to Lie, and then there's a constructive version that I did in my very first papers on moving frames with Mark Fels. And for infinite dimensional pseudogroups, it's a much harder result. Initial versions were due to Tressa. There's versions due to the other authors here based on things like Spencer machinery. And then there's a constructive version using moving frames that I wrote with a student of mine, Juha Pokian-Pelto, a former student of mine, I should say. Okay. So the key issues to be resolved, what I do not know is how to find a minimal basis of generating invariants. But what I do know how to do is what the structure of these invariant differentiations are, what are the commutator formulas, and how to construct the functional relationships among the differentiated invariants, what I like to call syzygies. And an example of these are the Kadazzi relations in surface geometry. Okay, so the recurrence formulas determine the entire structure, and remarkably, they can be explicitly constructed without knowing the formulas for the invariants themselves. So this turns out to be very powerful and can be programmed in symbolic manipulation. So now let me get back to basics in the case we're interested in, and let me first discuss the normal form for Euclidean plane curves. I have to keep track of, I still got time. Okay, so you think about it. You have a curve in the plane, you have translations and rotations, so you want to make this as simple as possible at a given point. So the idea is you use the translations to make the curve go through the origin. That's the simplest point on the plane. And then you can use a rotation to make its tangent line horizontal. Okay, so that's easy to do. At least you can picture that easily. And so the normalization is you set x and u to both be 0, and the first derivative of u is what's giving you. I'm assuming the curve is the graph of a function to make life simple. You assume its tangent is 0, and you end up with this as the Euclidean normal form. So because u and ux are both 0, the first term in the Taylor series for u in the normal form is the quadratic term, and the coefficient is up to a factor, the curvature. So this is the curvature we learn in calculus of a plane curve. The next factor is the derivative of curvature with respect to arc length. So that's the invariant differentiation. So that's the cubic term. And you think you know, when you compute these two, you think you know what's coming next, but it doesn't. It doesn't quite. You get the second derivative of curvature with respect to arc length, but there's this extra factor, this correction term. And these formulas, they get increasingly complicated, but you can generate them symbolically using the recurrence formulas from the moving frame theory. They're very easy to generate, certainly if you have a symbolic manipulation program at your side. Okay, so these come from the recurrence formulas. I'm not going to go through the details of how you do that because that's a whole lecture in itself. What about normal forms for Euclidean surfaces? So this is what we're really interested in. So we have a two-dimensional surface in R3. We have translations and rotations again at our disposal. So we can first translate the point on the surface to the origin. Then we can rotate the tangent plane to make it horizontal, in other words, in the xy plane. And then finally, there's an additional rotation around the z-axis that we're still allowed to do, and we do that to align the x and y axes with the principal direction. So this is where the principal curvatures come into play. So this is the normalization of the Taylor series that you end up with. And the full Taylor series, the Euclidean normal form, is of this form. So again, the linear and the order 0 and the constant and the linear terms in the Taylor series are all 0, and the mixed term xy is 0. So you end up with a coefficient of x squared and a coefficient of y squared, though exactly the principal curvatures. And then the next terms are derivatives of principal curvatures. These are the invariant differential operators. These are closely related to covariant derivatives, but they're not quite the same. They're less studied in surface geometry, but to me they're very important. And then you end up with a fourth order. You get, 5 differential invariants. Those you can obtain by invariant differentiation. And if you do it, you get formulas. You can actually invariantly differentiate 2 different ways, and you get these formulas. So the ones for I31 and I13 come from the commutation formulas for the differential operators. And the 2 expressions from I22 imply the famous Caudazi syzygy, the famous Caudazi relation in surface geometry. And one of the nicest proofs of Gauss's theorem about surfaces, that the Gauss curvature is an intrinsic quantity, comes from this equation, which is just a reformulation of the Caudazi syzygy. Okay, and y1 and y2 are what are known as commutator invariants. I haven't written them down, but they're there. Okay, for outlines, I'm going to take a normal form for the outline curve. I'm going to project down to it. So I'm going to assume, so the rim curve is parameterized by x, y of x, z of x. The outline curve is just parameterized by z of x. And we translate to the origin. We rotate around the normal vector, and we get the rotated normal form for the surface. So here are the principal curvatures of the surface, but this is sort of taking the normal form before and rotating it backwards. So I kind of undo it. So I still have the theta involved in there. If I implicitly differentiate the equation u sub y equals 0, I get y of x, and I determine z of x. Remember, those are the quantities to get the rim curve, and I get the outline curve is parameterized by this, and we get the normal form. Here's the curvature of the outline curve, and here's its first derivative. And if we substitute these formulas into the formulas for the derivative, we get the following beautiful theorem of Kunderink that says that the curvature of the outline curve is given by the Gaussian curvature of the surface, and this is the curvature of the curve obtained by intersecting the surface with a given plane. So you get these very pretty formulas coming out almost for free out of the normal form calculations. And so this is a well-known formula. The formula for the next differential invariant is less well-known, but is also to be equally interesting. Okay, so one starts to get these interesting invariants coming out. The last thing I want to talk about in the last 5 minutes or so is what I'll call, where do the outlines sit? So they sit in what I call the outline bundle. So let's consider RP2. This is projective two-dimensional space. And let's consider K as the tautological line bundle. In other words, it's the line bundle that for each line in two-dimensional projective space, K, the fiber above L, is just L itself. So this is a well-known thing in line bundle theory. The outline bundle is basically just the orthogonal complement to the tautological bundle. So this is the space in which the outlines sit, if you think about it. If we introduce coordinates, so I'm going to go fairly quickly through this, we put homogeneous coordinates on RP2, then the outline bundle is given by this space, so it's in RP2 cross R3, and it's given by this equation. Okay, and we could use inhomogeneous coordinates if we'd like. I won't go through the details. The Euclidean group, consisting of rotations and translations of three-dimensional space, acts on the outline bundle according to this very interesting action. So R is the rotation matrix and A is the translation vector. So the lines, you want to think of those as being the normal lines to the planes you're projecting on, are just rotated, and then the line bundle is mapped according to this very interesting action of SO3, or sorry, E3. A is the translation one. Here's explicit formulas. I won't go through them. There are infinitesimal generators for the group action. And so within this outline bundle, if you look at the collection of all the outlines of the body, that's what we use to reconstruct it. But now we're interested in how the Euclidean group is acting it. We end up with what I call the total outline. So this is a three-dimensional submanifold of the four-dimensional outline bundle, and we're interested in the action of the Euclidean group on this three-dimensional thing. So I've investigated this quite a bit, but I haven't finished up. I have a preprint that I posted on my website, but there's still a lot remaining to be done. One of the goals is to understand the differential invariance of the outline, and then to use that to reconstruct bodies modulo the Euclidean group. And so I know what the differential invariants are, and it turns out they're in the normal form, you get one differential invariant of order 1, and then you get 6 of order 2. So that's a lot of invariance, but it turns out that the recurrence formulas coming out of the moving frame calculus enable you to reconstruct all of them, all 6 of the second order invariant from a single first order invariant. So I'm going to skip over this because I've run out of time. The algebra differential invariance of a total outline is generated by this single differential invariant, and there are explicit formulas for this through invariant differentiation. And so a signature, which is what you use for solving the equivalence problem, can be generated by I, and its invariant derivatives of order at most 2. And then one can talk about symmetry groups or symmetry groupoids, because they're local symmetries. They're not global symmetries necessarily, but I don't have time to go through that. And plus, I have not fully done the details. There's a lot of calculations, numerical implementation of this that remains to be done. And so there's some references, reconstruction of surfaces from point clouds. There's the 2 papers that I have. Oops, there's a typo there, I just noticed. And some further references on moving frames and This is the two-dimensional case that I did with one of my other former students, Irina Kogan, and what she did with some of her collaborators. So thank you very much for listening.
Thank you, Peter. Please thank Peter for the beautiful lecture. Questions. Questions for Peter. Let me ask about still the smooth case, but the simple situation in the plane. So when we
Yes.
project a closed and say even convex curve to a line segment, so to many line segments,
Yes.
to
Yes.
along
going back
all
to the picture.
lines. So there is a connection with the famous challenge exposed by Richard Feynman. Do you know the story with the space shuttle? Space shuttle that failed, and then there was a big investigation.
Right, right. It was the what was it? What were they called? Something failed in it, the seals.
Yes, indeed. So the problem was to around this steel thing was manufactured but checked incorrectly for roundness, and the check was only what the diameter in every direction was exactly the same.
Right, right.
Right.
Which is not enough to characterize a circle.
A round circle, because there are other curves with this property, but not round circles. So in your case, you are reconstructing a curve from some extra information, right?
So I'm reconstructing it. So it's not just the length of the segments that's fixed. It's where the endpoints sit on the line. So that will be different. If you take one of these curves so I know this well because when I was I think a high school student or junior high school student, I did a little project on these curves of constant width and even constructed out of plastic some of them myself for this project. So one of the very first things I did. Yeah, so if you take one of these curves of constant width, so the lengths of those segments are all going to be the same, but where they sit relative to the origin. So remember, this is not quite the picture I have. The lines are all going through the origin. And so I take the coordinate. So if the origin is say in the middle, and I take the coordinate BL, so that's rho of theta, because theta is how the line is measured. As you go around, if it's a circle, the rho of theta is always constant. But if it's a curve of constant width, the rho, even though the length is fixed, the segments are kind of moving around. They're not all centered at the origin.
Right. Yeah, that's the difference.
So that's the difference. So that's what they should have been using rather than yeah, that's a great. I should add that to this talk, Feynman's
Indeed.
story about.
However, could I ask a related question? These curves of constant width, with your approach, or maybe it was done already, is it possible to somehow characterize all of them? All curves of constant width?
That's a good question. I don't know. I don't know the answer to that question.
So it might be still open.
It might be still so, or maybe this solves it, and this is known. So I would say so. So there's this. Where is rho of theta? Yeah, here it is. Rho of theta is minus sigma theta plus pi. So for it to be of constant width, I guess rho minus sigma has to be a fixed number. So it's possible, I'd have to think about this, so rho minus sigma is fixed and rho and sigma satisfy this. So there's a single equation involving rho. It's two values at theta and theta plus pi. That the length of that interval between those 2 points has to be constant. And that may be enough to characterize all curves of constant width. Yeah, I haven't thought about that. That's a really good question.
Okay, okay.
And I would assume this is known, but who knows?
Right. Yeah, very good.